Hello everyone, this is Iris Miano, your professor for Math 50 Pre-Statistics. I wanted to make a short video covering section 8.1. Although this material will be discussed prior to you taking exam 1, it is not part of the exam 1 material, so therefore it's not part of what I'm calling unit 1. Just to be clear, you want to be focusing on sections, let me list them off, looking at my day-by-day schedule. The sections you want to be studying for exam 1 are R1, R2, 1.1, 1.2, 1.6, and 1.7. Okay, in any event, let's go ahead and start off chapter 8, which is the beginning of unit 2. And let's start by defining what a term is. A term is an element in an expression that is separated by either addition or subtraction. Let me go ahead and write that down for you. We'll add some notes. An element in an expression that is separated by addition or subtraction. It's very easy to confuse the words term and factor in regard to talking about algebraic expressions. A term then should be distinguished from a factor by the operation that it's associated with. The operations of addition and subtraction signify or categorize terms, whereas factors are items that are separated from one another via multiplication or division. Moving on to some commutative laws here. Both addition and multiplication operations share the law of commutativity, which is just to say it doesn't matter in which order you add or subtract items, in which you add or multiply items, you're still going to get the same result. So generically, we can just go ahead and say any two items being added, let's call them A and B, it is equal to adding them in the reverse order. Similarly, A times B can be multiplied in the reverse order, and we're still getting the same value. That is how these two operations, addition and multiplication, exhibit the commutative law. Okay, let's go ahead and use the commutative law to rewrite the expressions given in these next 4 examples. So notice that the operation in question here is to focus on is the addition. So we're going to switch the positions of the 5 and the 4x. That's one way to do it. Alternatively, you could have focused on just the 4x part and switched the positions of the x and the 4, maybe use a raised dot to go in between them. But I'm going to assume that the intention here was to focus on addition as being the commutative item. So let's go ahead and now tackle number 2. This is where it can get a little tricky because I know what you're thinking here. You're probably like, oh, well, this is subtraction, and I know that the commutative law does not work for subtraction. I cannot simply change the position of the items being subtracted and expect to get the same answer. For instance, let me give you a simpler example. Let's say you had 2 apples and you ate one of them, so you're going to try and illustrate that with subtraction 2 minus 1, right? Now, switch the position of those things. Is 2 minus 1, answer being 1, is that the same result as 1 minus 2? No, not at all. The result there would be -1. So anyway, the only time you would be able to change the position of terms and have them give the same result is for addition, not subtraction. However, to make a long story short, we can rewrite any subtraction into addition. Watch this. So I'm going to put a note to the side, rewrite as addition. Here's the trick, guys. Every subtraction is addition of the opposite in disguise. And once these two items, let me write that plus sign a little bit more clearly. Let me try that again. Better. Okay, so once the subtraction is rewritten as addition, I can switch the position of the two items, and then that'll give me negative 8x squared plus 3. And plus is real wonky. And yeah, then that'll be what I put in here. Okay, and also you may be wondering, well, hey, from this step to this step, why did the negative 8x drop its parentheses? You can certainly keep them at that previous step, but go ahead and drop them by the time you write your final answer for using this commutative law, because that expression with the parentheses is it has extra clunky notation that's unnecessary. Those parentheses aren't hiding or aren't keeping anything in that's terribly important, so they can be dropped at that point. Okay, let me know if you have any questions about number 2. Number 3, on the other hand, we can switch the position of the P and the 4. Probably it's customary to have a raised dot in between these two in order to separate them. It's unconventional to have a variable next to a real number factor just next to each other, unless of course the real number factor is in front. Then it's conventional to have no operation in between, like you see in the original expression of just 4p. So switching them using the commutative law, go ahead and make sure there's a raised dot in between them. Here we have two binomial factors that are multiplied together. So in order to use the commutativity of multiplication here, let's say that that's what we wanted to do, we could just have x minus 3 quantity come first and multiply by x plus 2 later. Okay, great. So again, addition and multiplication. You can commute or switch the position of the two factors in question, or if it's multiplication, or the two terms in question if you're dealing with addition. Okay, let's talk associative laws. So addition and multiplication also follow the law of associativity, which is to say that if you have 3 or more elements, and some of them are grouped together with the incorporation of these parentheses, as you see here, you can pick up and move those parentheses to be around other terms, and you're still going to get the same result. So remember order of operations. They say grouping symbols first, so if you are going off of the left-hand side of the equation here, you would add B and C first and then add A. What the associative law of addition is saying is that it's the same as adding A and B first and then adding C later on. Same is true for multiplication. So let's have A outside of a BC multiplication situation. The associativity of the operation of multiplication dictates that you can multiply A and B first and then multiply by C after the fact. Let me go ahead and erase that dot right there. Cool. Let's go ahead and put it into practice. Using the associative law here, you might recognize for this first one that something tricky is happening. There is not addition all the way through, right, in this expression. We have an instance of subtraction. So do what you did, like in number 2 in the previous set, and change that subtraction into addition of the opposite. Then all of the operations in play will be addition, and you can use the associative law. The associative law does not translate to subtraction, just to be clear. So rewrite as addition. It's going to be my note here. We have 3x plus negative 5. So you're going to have multiple grouping symbols here, an outer parentheses and an inner parentheses, and that's fine. It's 2y. So now you can take these outer parentheses and pick them up and move them. I'll show some work, right? Oh, excuse me. Go back. Let's erase this right here. Okay, so now it can be 3x plus negative 5, parentheses around that, plus 2y. But you might be noticing that these inner parentheses right here are technically unnecessary, so you can drop them at this point and just leave it as 3x plus the quantity negative 5 plus 2y. And there you have it. We have successfully used the the associativity of addition. There was a little bit of a pre-game item that we needed to address, and that was turning that instance of subtraction into addition. That's what allowed us to use the associative law of addition. All of the operations between the terms need to be addition in order for you to use this law. Now notice for this next exercise, there's 3, 4, and x. All three of those factors are being multiplied. The 4 and the x first, the 3 and the 4 later. So let's go ahead and multiply the 3 and the 4 right away. That's a raised dot right there. And then let x multiply after the fact. I'm just going to go ahead and rest x next to the quantity 3 times 4, and that's perfectly fine notationally. There's no need for me to put a raised dot in front of the x, although it is not wrong to do so. Okay, great. So let me know if you have any questions about those laws. Let's introduce one more law before we do a little bit of mixed practice, and that is the distributive law. So I'm going to go ahead and just for fun mix up the color scheme and show you what I like to do in order to illustrate the distributive law. I actually like to draw arrows indicating all the places that this factor a gets multiplied inside of this sum b plus c. So I generally like to do this kind of a deal. Okay, so that'll indicate that a multiplies by b, and then I add a multiplied by c as well. You distribute. It's all in the name, folks. You distribute this factor of a over the sum b plus c. Okay, so let's go ahead and, if we understand that law and the ones previously mentioned, let's go ahead and use them in order to find the products. Mostly the distributive property, actually. So let's go ahead and I'll switch it back to this bright green because that was fun to use. And let's go ahead and take this 4 and distribute it here and there. And that will allow us to find the product for x minus 12. Everyone okay with that? The second longer distribution yielded a 4 times 3. And so that's how I'm getting the 12. The negative sign or subtraction right there just kind of comes along for the ride. Now, can we subtract a 12 from 4x? No, we cannot, because they are not like terms. So let's go ahead and just box that up as our final answer in the product there. All right, distribute once again. This time the signage is just going to change. This is what happens when you have a negative sign in front of a quantity. You change the sign and operation of everything inside. So that will give us negative x. It was plus 3 before the distribution, and now it turns into the opposite operation of subtraction of 3. Excuse me. Let me go ahead and try that one more time. That's 3 that goes there. And set there. Great. Moving on to number 2. Oh, I did these out of order. Did you notice I did numbers 1 and then 3? LOL. Here I go. Now tackling number 2. Albeit a little bit out of order, and I'm going to distribute this 3 over 3 different factors inside of this quantity. So that will give me, well, what's 3 times 6t? That's 18t, plus 3 times 5w, 15w, minus 3 times 8, that's 24. Notice that none of these 3 terms after the distribution property was implemented are like terms, and therefore nothing can be combined. So go ahead and box it up and call it good. And finally, for number 4, let's distribute the entirety of this factor out in front. Negative 2/5 goes here, and it goes there. Here, for this one, I'm actually going to show a little bit of work. Otherwise, the things that I had done previously were more or less done in my head, but here I'm going to go ahead and choose to show a little work. Let's have that negative 2/5, and it's going to explicitly be multiplied by 15x, and then I will subtract, so have this operation here, but then we're going to need a factor of negative 2/5. Go ahead and put that inside of parentheses. That's the wise thing to do, and then there's still a factor of, raised dot, 25y. So notice that I put my 15x and my 25y kind of up high. or in line with the numerator of these fraction parts, that's not by mistake. I'm doing that on purpose. Furthermore, if it's helpful, go ahead and put those items over a 1. Any integer term or instance in which you don't have a fraction, any term that's not a fraction can be forced into a fraction by throwing it over a 1. Okay, so this is just a little bit of trickery that I find to be helpful, and in doing so, I recognize that some common factors can be canceled across the way. So here, this 5 and this 15, they share a common factor of 5. 5 divides itself the once, it divides 15 3 times. So for this first term, everything's going to settle down to negative whatever 2 times 3 is, and then an x comes along for the ride. That'll end up being negative 6. Here, addressing the second term, notice that you're subtracting a negative factor, okay? Those cancel out and it's going to turn into addition. And also this 5 in the denominator is going to cancel with this 25 in the numerator. And these are the leftover factors. We still have a 2 and a y, and then of course this 5 left over. So this will end up being plus 10y. And here we go. Let me go ahead and rewrite this now. Cleaning house. Again, negative 2 times 3 times x is going to give me negative 6x. This operation turned into addition. And the leftover factors are 2 times 5 times y. That's 10y. And there you have it, folks. Distribution, but then also some algebraic simplification along the way. Okay, let's talk about combining like terms. What is the idea associated with combining like terms? Well, you need to look at the variable part of the term, and it needs to match up in order for you to combine like terms by virtue of the letter that's being used if there are variables, and they have to be raised to the same power. And the way that you combine like terms is you add the coefficients together, okay? Taking into account that some coefficients might be negative if they come in the form of a subtracted term, okay? So we will be adding, let me get a good color that's going to show up really well. We will be adding like terms, or sorry, not, I didn't want to write it that way, adding coefficients when variables and their exponents match. For terms. So saying that the variables and their exponents have to match is what we will want to keep in mind and distinguish between like instances in which you have like an x squared term versus an x term. Yes, in those instances, and it is going to come up for us, an x squared term and an x term are not considered to be like terms because their exponents don't match, okay? So you will not be adding x squared terms to x terms, or y to the 5th power terms to y to the 2nd power terms. You know what I mean? Even though the same letter is being used, the exponents have to match as well in order for the like terms to be combined, okay? So one thing we can do in practicing combining like terms, particularly for this first example, is to focus on, and we can color code this. I will color code this in order to make it really stand out. I like to collect all of a particular type of term by a certain color. So let's have 4y and subtracted off 2y. I'll underline those in the pastel green. Furthermore, this pastel blue color, I'm going to designate that for the constant terms. Now that's the terms that don't have any variables at all. If you don't have any variables at all, you are considered to be a constant term, and all of the constant terms can be combined. Lavender, we'll go ahead and designate that for the x terms, okay? So all the terms of a particular color are going to be added together. So let's start with the y's. I have 4y's over here and then negative 2y's over there. So you can liken this to being along the lines of 4y minus 2y. If you have 4, yellow backpacks and 2 yellow backpacks are taken away. How many yellow backpacks do you have? I know that's a really bad example. I'm just thinking about my daughter's backpack is yellow, and Y is yellow. Okay, our yellow stands or starts with the letter Y. Anyway, there are 2 Y's left, is all I'm saying, 2Y. Okay, moving on to the constants. -2 plus 5, plus a positive 5, that is. That will yield a positive 3, so we're going to add 3 as the next term. And then the last term will be the combination of all the x terms. We have 3 x's here, another 3 x's here. They're both positive. Add them together, you'll get 6x. So again, if we wanted to like color code them, here's the y's, here's the constants, here's the x's, just to put them back into their, you know, color coded glory right there. But yeah, it's not necessary at all that you use color coding. I just think it's probably a little bit useful in this first couple of endeavors. Here, we can go ahead and distribute this 0.2, which I think would be a great idea as a first step, and then you combine like terms, okay? And anytime this is the case, when you're asked to combine like terms and there's a distribution step that needs to happen first, always do that distribution step first, okay? So we will get 0.2 times 4.1. You can use your calculator for this bit. In fact, I'm going to go use a calculator just to make sure that my calculations are accurate. So that'll be 0.82 x for the first distribution, and then minus, what's 3.6 times 0.2? 0.72 minus 5.3. Okay. So at this point, you might notice that we have some like terms. I'll put them in this like peach color of this term and this term. So you can go ahead and combine them, taking into account their signage, okay? They're both negative terms, so you should have a larger negative final answer, okay? And this x term in the front here, it doesn't have any other x terms to combine with, so it's just gonna come along for the ride, okay? So this will be 0.82x minus, what is plus 5.3, and that'll be negative 6.02. Okay, so that's just adding these 2 negative numbers together. 2 negative numbers added together should make a more negative number, so to speak. Okay, go ahead and box that up for you. All set for those. We have one last page to cover, and it is translating sentences. We already covered some translation beforehand, so we're going to continue on this endeavor. Let's translate the following into an expression and let x be the number. So when it says a number or the number, we're going to let that be represented by the unknown of x. And then, of course, we're going to be asked to evaluate the expression after the fact as well. Let me go ahead and change the color for fun. So this translates as the number, okay, x, minus. That's an operation. And it's an operation that has, what's the word I'm looking for? The order in which the things are given are intuitive to the translation. So the only time that I've really seen in a lot of these examples where the order is, reversed from what it's given is the phrase less than. Okay, so we'll get into that a little bit later on as it comes up. So anyway, you can go ahead and directly translate this to x minus the product of the number and 3. So the product is another, keyword, and the number and 3, well, you should represent that as 3x. And you can have a raised dot if you want to. The number is going to, of course, be that x again. 3 translates into, of course, this coefficient of 3 here. Okay, so this, therefore, gives you the expression that you want, 3 minus 3x. You can have the raised dot there or not, and evaluate the expression of x equals 2. So when x equals 2, that's going to be 2 minus 3 times 2, which is, 2 minus 6, which is negative 4. So that's going to be the final answer for evaluating that expression at that particular value of x equals 2. Okay, we have a couple more examples of this with different sentences. So let's go ahead and tackle those. And if there are any questions on this, of course, we could talk about it in class, or we can wait to really formally discuss this until after exam 1. You guys will be the judge on that. It'll depend on how many questions you have about exam 1 material. The number minus 5, so again, the number, that's going to be your x minus 5 times the sum. Sorry, let me point to all of these things. When you are multiplying something by a sum, this sum really dictates that you have an addition happening between two elements. And if you are multiplying, that's what times means, right? So I'm going to put a raised dot so I have something to point at here for this operation. And then the sum really dictates that you have to put an addition symbol here inside of some parentheses. So I'll go ahead and just kind of like point to all of those three elements in order to illustrate how the sum is being translated here. So the sum of what? The number, so that put the x in this first position, and 2, which goes there. Okay, so that'll give us this entire expression. And evaluate, it says simplify the expression. Oh, here we're not even going to evaluate it, we're just going to simplify it. So let me go ahead and rewrite it over here. I'm going to leave out the raised dot, it's not necessary. So we should distribute first. And if there is, oh, and be careful, because you want to distribute a negative 5 here and let that be absorbed into the operation that now comes up in front of this first term in the quantity. And that'll give you x minus 5x minus 10, okay? So the sign and the operation of everything inside changed by virtue of the factor being distributed is negative, okay? There's an instance in which we can combine like terms right here, right? These are both the x terms, and then there's a constant term that's just going to be waiting in the wings there. X minus 5x, well, hold on, this is actually a 1x, right? If there's a coefficient here that could be explicitly reported, it would be a 1, but anytime you have a coefficient of 1, it's just the default, not expressly represented coefficient. So what's 1x minus 5x? Well, that'll be negative 4x. And then, of course, we'll subtract off the 10, which just, as I like to say, comes along for the ride. Okay, last one, and then I'll let you go. Twice the number. Twice, that means 2 times the number, which is this right here, plus 9 times the difference. Okay, so twice the number, and then comma, a little bit of a pause, plus, that's this operation here, 9 times the difference, 9 times, so 9 goes there, times, I guess I'll squiggle it, the difference. Okay, so we're multiplying by an operation of either a sum or a difference, so we need to have parentheses and subtraction. So the difference really is being illustrated here, there, and there. Okay? And the difference is one of those straightforward translation phrases for subtraction. The first thing mentioned is going to go in this position, the number, call it x, and 4, which just goes as the thing that's being subtracted off. Okay, so that makes the entire expression, and let's go ahead and simplify it. We'll do that in green. So I'll rewrite the expression of 2x plus 9, leaving out the raised dot, x minus 4. And let's do very similar to what we did in the previous problem. Distribute first, and we will be left with 2x plus 9x minus 36. The x terms can now be combined, and it looks like it'll give me 11 x's altogether. 2x plus 9x giving me 11x minus 36. And that is my final answer, addressing the prompt to simplify the expression. Okay. That is all for section 8.1. Remember, 8.1 is not a part of exam 1 material, okay? It'll be part of unit 2, which will be associated with exam 2 material that we will get into after you guys complete exam 1. Good luck on exam 1, everybody, and let me know if you have any questions on this material, either on the day that we have slated to cover it or after, of course, after exam 1 would be perfectly fine as well. Thanks a lot, guys.